So we've discussed the first and second lines of defense, and we're going to start talking about the third line of defense. But one of the things that I wanted to point out before we get there is this idea that even though we talk about these things separately, it's really the easiest way to talk about all of them. When you actually look at what's happening during an immune response, it's really an interaction of everything. So you have your innate immune system that we already talked about, but then you have your adaptive, antigen specific, your third line of defense that we're going to be talking about next. So all of these things are supposed to work together in tandem in a healthy individual to help clear the infection. So our third line of defense majorly consists of two types of cells, B cells and T cells. B cells and T cells are made in the bone marrow, and T cells will leave and go to the thymus to become mature. B cells will become mature within the bone marrow. Once they're mature, they can then leave, and both B and T cells will transit through the blood and go to organs like the lymph nodes, the spleen, etc. So that third line of defense, our adaptive immune system, this one uses specific cells, those B and T cells I just talked about, but it learns about every specific single infection that you've had. So it reacts to the specific proteins or other molecules that are on the surface of the organism trying to cause an infection. So here they're showing a bacterial cell, and so bacterial cells will have lots of different things on the surface, and they're trying to illustrate with three different color shapes. They have a kind of orangey square, a red triangle, and a beige, I don't know, like half oval. I don't know what you would call that shape. But each of those is a specific antigen or a specific molecule on the surface of that cell. When you mount an adaptive immune response, you don't form the immune response against the bacterium. You actually form an immune response against red triangle. So you'll have some antibodies and some cells that are specific for red triangle. You'll have some that are specific for this orange square. And you'll have some that are specific for this beige half oval. So our specific adaptive third line of defense is very specific. It reacts to certain parts of the molecule. And as you see in this cartoon, you can have molecules or cells that will react to the triangle and that will react to the half oval, and they can help work together to clear that infection. So when we talk about the adaptive immune system, we really highlight the idea that the adaptive immune system is very specific. So yes, it's interacting with an individual pathogen, but also it's interacting with very specific molecules on the surface of that pathogen. The other really great thing about our adaptive immune system is that it has memory. It remembers, right? It keeps some cells around that were made in response to an infection, so that if your body ever sees that infection again, it can very rapidly replicate those cells, make more antibodies to help you clear the infection even better. This is kind of the principle behind vaccination. Vaccination tricks your body into thinking that you've had an infection, so you make the memory. And then if you ever see that infection again, the memory can help keep you from getting sick at all, maybe help you get less sick so the disease is less severe or the disease ends faster. The other thing that your antigen-specific immune system should have is what we call tolerance. And that means that your body technically should recognize, so your immune system should recognize all of your immune cells, your immune cells should recognize your body as itself. So your immune cells will look at all of your cells and it should say, oh, that's me, that's me, that's me. So it can discriminate between a foreign antigen and a host antigen, your own antigen. In patients who have a failure of tolerance, if their immune system starts to recognize itself, that's when you get autoimmune conditions, lupus, multiple sclerosis. Any number of autoimmune conditions is because the immune system recognizes your own cells as bad. When we look deeper into the adaptive immune response, we have two different kinds of cells. We have B cells and T cells. And so really what we do is we split the adaptive immune response into what's called humoral and cellular. So humoral is mediated by B cells. And what happens is these B cells will be activated, and they get activated by a T cell. So even though we talk about two separate facets of the adaptive immune response, they still do work together. So the B cell will recognize an antigen. This B cell in particular recognizes yellow square, and it gets stimulated by a T cell, and then it turns into this cell called a plasma cell. So a plasma cell is just a B cell that has changed into an antibody producing factory. And so this antibody producing factory will now produce all of these antibodies to circulate through your bloodstream that will all bind to yellow square when they find it. And then some of these B cells that recognize yellow square will turn into memory. So if you ever see yellow square again, they can quickly turn into these plasma cells and make more antibodies. On the cellular side, you're looking at T cells. So T cells get activated because they'll bind to one of those phagocytic cells, like a macrophage or a dendritic cell. And then when they get activated, they can do a number of different things. They can activate B cells, they can activate macrophages, or depending on what type of T cell it is, they can actually kill the infected cell. So it's really important that you have all of these factors working together. You have those T cells that can activate lots of things, the T cells that can kill infecting cells. You have B cells that produce antibodies that can neutralize any antigen that's in the bloodstream. And in patients who have immune deficiencies or are immune compromised, sometimes what we see is relatively mild. Maybe they can't make one type of antibody. We have lots of types of antibodies. Maybe they can't make one. Okay, they're going to be fine for the most part. But we have some patients that can't make any of these cells at all. And those patients are at really high risk of getting fatal infections. Again, just to illustrate that principle of specificity, this immune cell, whether or not it's a B or a T cell, only will bind to the red triangle. And then you'll have a different cell that will bind the square. You'll have a different cell that will bind the oval. So it's very, very specific. And then, of course, you have this concept of memory. You'll have immune cells that remember, hey, do you remember that one time we got infected by red triangle? Oh, red triangle's back. Let's go. And then you have that idea of tolerance. You can see the receptor here is supposed to bind to the triangle. This one binds to the oval, but we look like a square. Well, these cells aren't going to recognize the square, so we're good. The immune cells won't recognize us. Briefly, to talk a little bit more about antibodies, they're proteins that are made by B cells. B cells will become plasma cells, which are basically just factories to produce as much antibody as possible. Antibodies also belong to a class of proteins called immunoglobulins, IG. So they interact with pathogens, they bind to pathogens. They can be found in blood, right? So serum is the like the plasma component of blood. They can be found in breast milk, gastric secretions, vaginal secretions. They can be found all over the body. There are 5 major classes of antibodies, and they're found, this list here is in decreasing order. So we have mostly IgG, very little IgE. And we all produce billions of different kinds of antibodies because every time we see a pathogen, we can make antibodies against all of the different parts of that infection. I picture antibodies, to me, they kind of look like a little person, like doing the YMCA, right? They're holding up their arms like, yay. So here are the arms, and then here are the feet, the legs. At the very end of the arms is where you have your hands. This part of the antibody with the hands is where it will grab onto the antigen. And then the feet are constant. So it always will have the same legs. Every class of antibody will have the same type of legs, but the hands are different because they all can grab different things. So our different types of antibodies, the first we'll talk about is IgG because it's found at the highest levels. It's found in all your tissue fluids. It's found in your plasma. It can activate this system called complement, which basically punches holes in infecting cells. And it can defend you against lots of different things, bacteria, viruses, and toxins. But also IgG is really important because it can protect the fetus and the newborn. So it can be the antibody that crosses the placenta to protect the fetus from infection. And it also can be found in breast milk, and it can go through the tissues of the newborn's GI tract to protect them. So this is the antibody. This is the reason they recommend that mothers are fully up to date on their vaccinations so they can share some of their antibodies with the newborn. IgA is another really important antibody. It's found at lower concentrations than IgG, but it's mostly found in secretions lining your GI tract, the urogenital tract, and it defends against bacteria and viruses that are trying to get in. IgM is only really found in the blood, in the plasma component of the blood. This is the one that if you get a blood transfusion from the wrong blood type, that will cause the issue where it will lead to the destruction of those red blood cells that have come in. So it's why they always want to match you with the appropriate blood type if you ever have a blood transfusion. And it can also activate that system that punches a hole. So what can happen is if you get blood that isn't your blood type, this antibody, this IgM, will bind to it and cause those holes to be punched in the new red blood cells, which shouldn't happen, but if you do the wrong one, it will. IgD is only really found on the surface of B cells, and it helps to activate them. So it's not secreted, it's not floating around your bloodstream, it's just attached to the B cells. IgE is also found in secretions. It's found at very, very low levels. It promotes a lot of inflammation, and it's also responsible for when we have allergies. So those of you who have allergies, you can thank IgE for that. So what happens is, just very, very briefly, antibody production starts when you are exposed to an antigen, and that is recognized by B cells. And eventually you just get tons and tons and tons of antibody produced. So those antigen stimulated B cells will multiply and multiply and multiply. Hey, we saw the red triangle, let's go. And they will turn into plasma cells to produce boatloads of antibody, and memory cells to say, hey, when we see that red triangle again, we got this. And that's called your primary antibody response. The memory cells, hey, you remember back in the day when we saw the red triangle? They can live for years. And when the red triangle comes back, they can quickly transform into cells that will secrete antibodies again. And that's your secondary response. Antibodies in the body, what's the point? So they bound to an antigen. Okay, how does that help us? It helps us in a few different ways. So the first is called agglutination. So what can happen is, here they give an example of IgA. You have a bacteria that's produced a toxin, and the IgA, you see it grabs all the toxin, and you can have multiple antibodies holding on to it. And when you get this type of clumping, it's a lot easier for the phagocytic cells, like a macrophage, to recognize it and chomp it up. You can also have complement. So there's a couple of different things that can happen here. The antibody can do what's called opsonization. So basically you have this bacterium, you have all these antibodies that bind to it. And again, that triggers the phagocytic cells to say, ooh, yum. And then the lysis they're showing down here, they're giving an example of IgM. It binds to the bacterial cell, and that recruits everything that will cause the cell to be lysed or to explode. Antibodies, and they don't really, it looks a lot like agglutination, basically, where you get this complex that forms. But so the idea behind neutralization, they call it that specifically when it's toxins or viruses, because not only does it cause that kind of clumping, but it prevents, so it neutralizes the toxin or the virus by preventing it from binding to the cell. And then here we can see the difference between the primary and secondary response. When you first are exposed to an antigen for the very, very, very first time ever, it can take time for that response to occur. And the first antibody you'll get would be IgM, and then you'll start to get IgG that are both specific for that particular antigen. The next time you see it, you get less IgM, and you get tons of IgG, and it occurs a little bit faster. So it's faster and it's more intense.